Short and easy class today. Short and easy, that is, if you're fairly familiar with the ideas behind it, that is the idea of a parametric curve and what that looks like, and with the ideas that we have developed in the last few classes regarding areas and how to compute them using definite integrals. So what are we talking about? What we're going to look at is how to compute the area bounded by a parametric curve. Now, remember what a parametric curve is? Is a curve which is not defined through a single function y equals f of x, but through two functions, x and y, both being functions of some parameter t. And we use t normally because we represent time. Now, these curves, if you remember, are used primarily in situations where we're trying to describe curves which are not actually functions in the regular sense of the word. So in other words, y equal function of x does not pass the vertical line test. However, we can use them also for situations where we are dealing in fact with a function, and when not, we can always split our curve into several pieces so that each of them, at least locally, is going to be a function of x. So all of these things are things that you may want to refresh your memory on from the full term, and make sure that you're fairly clear on what these represent. Now, the only case involving parametric curves that we're going to consider is the situation where the region is actually a standard one, except, so bottom is on the x-axis, the two sides are vertical lines, except that the top curve is not described through an explicit function y equals function of x, but through a parametric curve. Now, in this particular situation, then the solution to the problem is fairly easy, and in fact I'm going to show you in a minute, and that's why this class is going to be short. In this case, all we have to do to find the area of a region like this is just make a change of variable. Remember that what we're looking for is the integral from a to b of f of x dx, except we don't know what f of x is because our function or our top boundary is not given as a function f of x, but as two parametric functions. So in other words, we know that there is a function there, but we don't have a formula for it. Well, what we're going to do is we're going to change this integral from the way it is right now to another integral which is entirely in terms of t. So how do we do that? Well, first of all, we notice that the role of the function in the definition of the definite integral is that of providing us with the heights of the approximating rectangles that we use to construct the definite integral. But what is this height in this particular situation? Well, the height obviously is going to be given by the y-coordinate, and we know what that is. We do have a formula for the y-coordinate. So we're going to change that integral to the integral, instead of h, we're going to use y of t. Alright, what else is left in our integral? Well, the next thing that we need to worry about is the dx. But what is the dx? The dx is the differential of x. Well, we do have x as a function of t, and therefore we can compute what the differential of x is as a function of t. Remember, by definition, the differential is given by the product of the derivative times the differential of the independent variable. So our dx becomes simply x prime of t dt. Well, what about the limits? We have to change those too, right? Because now our variable is not x anymore, but is t. And so what are we going to do? Well, for a, we're going to look at our function and we're going to ask, all right, what value of t corresponds to the x value of a? So what value of t gives rise to the x value that we are looking for, the value of a? And that's what we're going to use as our bottom limit. And the same thing, of course, with the upper limit. We're going to ask, all right, what value t2 corresponds to the upper limit b, and we're going to place that particular value as the top limit. Now notice that as we do this change of variable, the t1 and the t2 may not necessarily be in the usual order. So t1 may be actually greater than t2, and that is fine. We don't want to switch them. We want to leave them as they are, otherwise we may end up with a negative area. So this is all there is to it, really. Now, for what about other more complicated situations where the region is bounded by a parametric curve, but is not in the standard shape that we're seeing right here. Well, we're going to use the same trick that we used to figure out the formula for the area between two curves. Okay, and that is what we're going to be doing is we're going to split the region that we're going to look at, so that in each case we're going to have one top function, one bottom function. Maybe each of them is maybe parametric on its own, and that's okay. We're going to make this change of variable on each one of those functions until we have everything in terms of t and in terms of computable integrals. This is it, folks. All we have to look for now is do examples and see how that works out in practice. And just to allay your fears, no, the examples are not going to be complicated.